Hey guys, hope you are doing good. In today's video, you're gonna see step-by-step guide for beginners about how to learn chemistry. So we begin with the first chapter, which is about properties and structure of matter. Uh, so we have the what chemists do, properties and change, classification of matter, structure and composition of material substance, a quick look inside the atom, number of subatomic particles, and homework exercises. So we begin with what chemists do. So chemistry can be defined as the study of the composition structure, the properties of material substance, and the change associated with the substance. The careers of chemists and chemical laboratory technicians consist of the study of the composition, structure, properties, and changes of material substance. So the fruits of their labor are many. The following items are just a few that have resulted from chemists. The laboratory technicians studying chemistry, so batteries, plastics, and clothing fibers, pharmaceuticals and medicines, pesticides and herbicides, clean water and air, fertilizers, soaps and shampoos, and perfumes and deodorants. How do we begin study of chemistry? So we begin by understanding what is meant by each item in the definition. So what is the properties and change? So let us begin with the word change. So a change occurs when a material substance undergoes a transformation in appearance or substance as a result of a process imposed upon it. When water is heated, it boils and is transformed into steam. When iron is exposed to air in the presence of moisture, it roasts. When crystals of sugar are dropped into a container of water, so the sugar dissolves. When gasoline burns, it is converted into carbon dioxide and carbon monoxide. In each of these cases, the transformation of some type can be observed. There are two types of change: physical change and chemical change. So we can the chemical change involves a change of some substance, for example, conversion of iron to rust, conversion of gasoline to carbon dioxide and carbon monoxide, while physical change is change that is purely physical, no change of substance. For example, evaporation of water, dissolving of sugar. Change of substance means that one or more substance have been converted into something entirely different. Clearly, the iron and gasoline examples represent the change of substance, while the evaporation of water changed from liquid phase to gas phase, and the dissolving of sugar changed from solid state to the dissolved state. For the properties of material substance are simply characteristics by which this substance may be described or identified. For example, a property of water is that it is a liquid. A property of silver is that it is shiny. Property of iron is that it roasts. A property of pesticide, such as mosquito repellent, is its disagreeable odor. Property of sugar is that it tastes sweet. A property of salt is that it dissolves freely in water. And the property of the chlorophyll found in green plants is that it is green. There are two kinds of properties: physical properties and chemical properties. Physical properties are physical characteristics that might be determined by simple observation or measurement and involve no chemical change. Most of the examples just listed, namely color, odor, taste, physical appearance, physical state, solid, liquid, or gas, and solubility are physical properties. All of these may be determined by simple observation. with one of the five senses, such as sight, for example, color, sheen, physical state, or smell, for example, odor, and other physical properties that require measurement, and some of these require calculations. Example are melting point, boiling point, and density. Uh, melting as 32 degree rise to water, and boiling point, the temperature is at which as liquid substance boils, such as 212 or 100 degrees. For water also require the measurement of temperature. Because of uh, these physical properties, because they are characteristics by which water may be described or identified through simple observation or measurement. So density is a physical property that indicates how heavy a substance is compared with how much space it occupies. So its volume, considering two metal blocks or of equal size, one made of aluminium and one made of lead, it is easy to understand the concept. The lead block is much heavier than the aluminium block, in spite of the fact that the blocks have the same volume. It has a greater density or greater mass or weight. For given volume, density is something that is measured and requires a calculation to know what is it. In a chemistry laboratory, it is easy to measure the weight of a quantity of matter, and it can also be easy to measure volume. Density is calculated by dividing the measured weight by the measured volume. So the density of lead is 11.3 grams per milliliter. This is a physical property of lead, a characteristic by which it may be described and identified. The density of aluminium is 2.70 grams per millimeter, and this is similarly a physical property of aluminium. Or the chemical properties are characteristics that involve chemical change. The chemical property of iron is that it roasts in the presence of air and moisture. The chemical property of hydrogen is that we combine oxygen to form water. A chemical property of chlorine is that it will combine with sodium to form table salt. A chemical property of gasoline is that it burns readily and is converted into carbon dioxide and carbon monoxide. Perhaps the most useful aspect of properties, physical or chemical, is the fact that they can be used for identification purposes. Chemists and chemical laboratory technicians are sometimes faced with the task of identifying an unknown material or material substance possess a unique set of properties. No two substances will ever be completely identical in all respects. So we move to the classification of matter. First, the introduction. So more than 13 million material substances exist. The study of the composition, structure, properties, and changes of this large number of substances is accomplished by creating classifications and subclassifications. The vast majority of substances, as they are found in nature, are not pure. In fact, they are often extremely complex mixtures. Examples are ocean water, oil, dirt, and ores, even air, and the fresh water found in lakes and wells can actually be complex mixtures. For example, ocean's water contains many substances beside water. Large number of industrial, household, and laboratory activities are dedicated to purifying or separating mixtures, substance or by substance. Examples are industrial processes such as the refining of oil into compound chemicals, household processes such as the removal of minerals from water with the use of water softens, and distillers and laboratory processes such as the use of sophisticated chromatography instruments to analyze the quantity of pesticide residue in river water. In many of these purification chemists, extremely pure substances often result and are available as consumer products or for further industrial or laboratory processing. Thus, while complex mixtures are commonplace in our lives, the same can be said about pure substance. A classification according to purity, mixtures versus pure substances is our starting point. So all matter can be classified as either a mixture or a pure substance. All pure substances can be classified as either a compound or an element. The flow diagram in figure 1.1 is a pictorial representation of this. We will now define these terms and give additional details and examples. So we have the figure 1.1, a classification for matter based on purity. As you can see, we have matter, pure substances, which give elements and compounds, and for the other side we have the mixtures. So we move to the elements and the compounds. So there are 109 elements in existence and more than 13 million compounds. Many of the elements are familiar to us. Examples include various metals such as iron, copper, aluminium, and lead. Also familiar are elements that are not metals or non-metals. Example of this are helium, hydrogen, oxygen, and helium. For convenience, all elements have been assigned symbols. A symbol consists of one or two letters. The first a capital letter, and the second, if you used a lowercase letter. These letters are derived from either the English name or the Latin name of the element. For example, A1 is the symbol of Al is the symbol of aluminium, and L is the symbol, and I is the symbol of iodine. In these two examples, the symbol is either the first letter or the first two letters of the English name. The symbol Fe represents iron and is derived from its Latin name, ferrum. Other examples are, for example, Cu from copper, the Latin word for copper, and A from yttrium, the Latin word for sodium, and Pb for plumbium, Latin word for lead. So all the 109 elements are listed in a table that chemists have developed, known as the periodic table. So the periodic table contains the names and symbols of all the elements, as well as some numeric information. So the numeric information will become important to us as the study of chemistry proceeds. However, for the present discussion, let us take a look at the periodic table and especially notice the names and symbols. An example of periodic table is presented in figure 1.2. So the periodic table is an arrangement of small squares, each of which can contain information about an element. Each square is part of the horizontal row and the vertical column. Horizontal rows are referred to as periods, and the vertical columns as families. The large letter or letters in the center of the squares constitute a symbol. Immediately below each symbol in the table in figure 1.2 is the full name, and the topmost period are the squares for the elements: hydrogen symbol H and helium symbol HE. Hydrogen is on the upper left of the table, as you can see here. This is the hydrogen. So first column group 1A, and the helium is on the upper right, last column group 8A. Notice the number is in the upper left corner of each square. The number is also known as the atomic number. So the atomic numbers are in numerical order, left to right, starting with hydrogen number 1 and continuing to helium number 2, then the second period for lithium number 3 and beryllium number 4 through 9 and number 10, and continuing to sodium number 11. In the third period, the other familiar elements we mentioned can be found as follows. Oxygen is in the second period, number 8, aluminium in the third period, number 13, iron in the fourth period, Fe number 26, copper in the fourth period, Cu number 29, iodine in the fifth period, I number 53, and the lead in sixth period, Pb number 82. So some elements are named after people. Examples are Einsteinium ES number 99 after Albert Einstein, Curium Cm number 96 after Marie Curie. Others are named after places. Example are Californium Cf number 98 after California, and Europium EU number 63 after Europe. Others have rather odd names, the origins of which are not immediately obvious. Examples are praseodymium PR number 59 and molybdenum MO number 42. Compounds are pure substance that are special combinations of two or more elements. The elements that are present in this combination are shown in a symbolic representation for the compound, which is known as its chemical formula, or simply its formula. The compound that is probably most familiar everyone is water. So water is a special combination of the elements hydrogen and oxygen, which is shown in the formula for water, H2O. Other examples of compounds and their formulas are sodium chloride, formula NaCl, a special combination of the elements sodium, Na, and chlorine, Cl. Calcium carbonate, formula is CaCO3, a special combination of the elements calcium Ca, carbon C, oxygen O. And potassium chromate, formula K2CrO4, special combination of the elements potassium K, chromium Cr, and oxygen O. One may ask, if compounds are combinations of two or more elements, why are they not classified as mixtures rather than compounds? The key difference between mixtures and compounds is the nature of this special combination. When two or more elements come together and form a compound, they lose their individual elemental identity, and the resulting combination exhibits properties that were not exhibited before the combination. There is a complete transformation of substance, a chemical change, or a chemical combination. Water is a great example. Hydrogen, a highly flammable gas, combines with oxygen, a gas which supports combustion to produce water, liquid that extinguishes fires, because water does not exhibit properties of either hydrogen or oxygen. So there has been a complete transformation of substance from the two elements into one. Therefore, water is a compound, we can make similar statements about sodium chloride, calcium carbonate, potassium chromate, and all the often other compounds that exist. The elements in a compound are chemically combined. The elements or substances in a mixture are not. They are simply physically mixed and retain all their properties. They can be separated by physical means, such as filtering. There are more than 30 million compounds is intergrain. Why so many? The answer is that a very large number of different chemical combinations can result from the use of the 109 elements that exist. The composition and structure aspects of chemistry are at the heart of the concept of chemical combination. As our discussions become more and more advanced in this and later chapters, our understanding of this fascinating concept will become clearer. So we have homogeneous and heterogeneous. All pure substances, example elements and compounds, are homogeneous. This means that their composition is identical throughout. Mixtures are not necessarily homogeneous. If the composition of a mixture is not identical throughout, then the mixture is heterogeneous. Examples of homogeneous mixtures are sugar water, gasoline, and stainless steel. Examples of heterogeneous mixtures are solid water sand mixture and chocolate chip ice cream. As indicated in section 1.3.1, compounds and elements are most often found in the natural world mixed with other material substances. It is thus important for us to include mixtures in our discussion. So mixtures may be classified as either homogeneous mixtures or heterogeneous mixtures, depending on how well mixed the mixture. Compounds are in a homogeneous mixture. The mixtures compounds are mixed as well as they can be mixed, such but you can tell that is a mixture when you look at it. In a heterogeneous mixture, the mixture compounds are not mixed very well, and you can tell that is a mixture when you look at it. There is no chemical combination of the compounds for mixture as there is with the elements that make up a compound. So we move to structure and composition of material substances. At the end of section 1.3.2, we indicated that composition and structure aspects of chemistry are at the heart of the concepts of chemical combination. Let us now begin to explore the meaning of chemical combination by looking more closely at the structure and composition of elements and compounds. So we have the structure and the composition of elements. Let us imagine a fictitious scenario for the analysis of the structure of material substances. Imagine that you hold in your hand a block of silver metal. Now imagine that you also have an extremely sharp cutting tool, one that is capable of cutting through metal. You proceed to cut the block of silver in half with cutting tool. Now you have two pieces of silver in your hand, both smaller but the original. You lay one piece aside and then proceed to cut the other smaller block in half. Following this, you lay half aside and proceed to cut the other side, still smaller block in half. Continuing to handle the increasingly smaller blocks and cutting them in half, you reach a point at which the block is too small to see very well. You obtain magnifying glass and proceed to continue halving, and then discarding until again you have a silver piece so small that you cannot see it adequately with the magnifying glasses. So you bring out your microscope, and perhaps with the smaller cutting tool you continue to cut and discard cut and discard, you then reach a point at which you cannot see the speck of silver even with the microscope set on its most powerful setting. So with the help of a chemist friend, you gain access to the most powerful microscope in the world, and you continue the cutting and discarding process. Finally, you get the point at which you can absolutely go no further. At that point, you have speck silver, barely visible through the most powerful microscope. The question in your mind is, how far would I be able to go if I could go farther? And so you start to dream and imagine that you have access to a microscope so powerful that you can see the tiniest objects that can possibly exist. Then you resume the cutting and discarding process, and you finally reach the smallest particle of silver that you can have, uh, such that if you proceed further to divide the smallest particle, you discover that it is no longer silver. The question is, what is the smallest possible particle, the smallest particle of an element that can exist and still be that element is called an atom of that electron of that element. The atom is most fundamental structural unit of all matter. As you can see here in fact, figure 1.3, looking at a uh, sample of an element through a powerful microscope that can only be imagined. Scientists believe we will see a stack of spheres that are the atoms of that element. Microscope image from Shutterstock.com. So the atom is the most fundamental structure unit of all matter. Uh, the fundamental unit of an element. Scientists most often imagine it having the shape of a sphere or ball. As we saw in the figure 1.3, all elements are composed of atoms. The atoms of each individual element are unique uh, to that element, which means that an atom of one element is different from an atom of any other element. However, atoms of a given element are very similar, but not identical. Chemists think of atoms as tiny spheres of balls. One measure of this uniqueness is the size of this sphere. Hydrogen atoms are the smallest of the spheres, and atoms of francium, Fr atomic number is 87, are among the largest. The francium atoms are over 9 times the size of hydrogen atoms. This is like comparing a ping pong ball to a basketball. The usually small sizes of all atoms, however, cannot be over emphasized, in spite of the fact that francium atoms are relatively large. It would take hundreds of thousands of them lined up side by side to make a line visible to the naked eye. For the structure and composition of compounds, dividing and discarding process like that just described for the element silver may also be performed on compounds, and the result would be similar: an extremely small fundamental structural unit visible only through our medical microscope. But when divided would no longer be that compound. The situation is more complex. However, because the nature of this fundamental unit is not the same for all compounds, some compounds are described as molecular or covalent. Others are described as unique. For molecular compounds, the fundamental unit or particle is called a molecule. For unique compounds, the fundamental unit is a grouping of ions that we can call the formula unit. An ion is an electrically charged atom or a grouping of atoms. The vast majority of the 13 million compounds that exist are molecular. That fact certainly does not diminish the importance of those are ionic. However, since there are some very common compounds in our daily lives that fall into the ionic category, chemical formulas which we've defined in section 1.3.2 as a symbolic designation for compounds are used for both molecular compounds and ionic compounds. Thus, we can tell what elements are chemically combined to make up a compound by looking at its formula. Examples we presented in section 1.3.2 included H2O, which is water, a combination of hydrogen H and oxygen O, and NaCl, sodium chloride or salt, a combination of sodium and and chlorine Cl. Water is an example of a molecular compound, while sodium chloride is an example of ionic compound. Since compounds are composed of elements in a chemical combination, it follows that molecules formulas units are composed of the atoms of the elements in chemical combination. Thus, molecules of water are composed of atoms of hydrogen in a chemical combination with atom of oxygen, and formula units of salt are composed of sodium atoms, actually ions, and chlorine atoms, which is ions in chemical combination. It is the nature of the chemical combination that defines whether a compound is molecular or unique. This will be detailed further as our study proceeds. The number of atoms of each element that make up a molecule or formula unit can be seen in the formulas. The numbers written as the subscripts in the formulas can be such as the 2 in the formula for water, H2O, and the 2 and the 3 and 4 the formula for potassium chromate, H2CrO4, represent the number of atoms of the elements immediately to the left of each subscript in the formula. If there is no subscript element in the molecule or formula unit, thus in the molecule of water, H2O, there are 2 atoms of hydrogen and 1 atom of oxygen that are chemically combined in a formula unit of salt, and ACl, there is one atom, which is ion of each element, sodium and chlorine, in a formula unit of potassium chromate, also an ionic compound, K2CrO4. There are 2 atoms of potassium, 1 atom of chromium, and 4 atoms of oxygen. Thus, chemical formulas are reasonable representations of molecules and formula units of which compounds are composed. A few elements consist of 2 atoms that form molecule of the element. Because of this, the symbol of this element is actually a formula that represents this the atomic situation. These elements are hydrogen H2, fluorine F2, chlorine Cl2, oxygen O2, nitrogen N2, bromine Br2, and iodine I2. Some formulas utilize parentheses. An example is the formula for calcium nitrate CaNO3, a grouping of elements enclosed by the parenthesis is an example of an ion, the nitrate ion, and it's placed in a parenthesis in order to maintain its identity in the formula. The 2 subscripts outside the parenthesis means that there are 2 of these ions in each formula unit of CaNO3 2. This formula would be equivalent to the formula CaN2O6, The formula with the parenthesis is preferred, however, because it gives additional information about this compound. The neutral ion is a common grouping of atoms in which one nitrogen N atom is chemically bound to 3 oxygen atoms. Without the parentheses, this small depth bit, a depth bit of information would not be communicated. We previously indicated that chemists think of atoms as tiny spheres of various size. Chemists think of molecules and formula units as entities that have a number of these spheres linked together or stuck to each other. The forces that cause them to stick differs depending on whether the compound is ionic or molecular. For example, a chemist's view of the molecules of water H2O is shown in figure 1.4. The size of molecules and formula units and are most often on the same scale as the incredibly small atoms of which they are composed. So for the figure 1.4, looking through a mythical microscope at a sample of a molecular compound such as water, we would see the molecules of what compound. Microscope image from Shutterstock.com. We have also a quick look inside the atom. We have stated that the atom is the smallest particle of an element that can exist and still be that element. We have also stated that if an atom is split in an attempt to make a smaller particle of an element, we would no longer have that element, but instead would have something else. We would have a collection of subatomic particles called protons, neutrons, the electrons. These are the major particles of which all atoms are composed. Scientists discovered the existence of these particles and their properties in the late 80s and early 90s, when some interesting experiments were performed. The model theory describing these particles, especially the electrons, as is complex and highly mathematical in our present discussion. A very brief physical description of these particles is presented. So let us begin with the mass of these particles. Mass refers to the amount of a material. This amount of material is measured on the Earth's surface by measuring the effect of the pull of gravity on it, or in other words, it's with references to mass in this discussion can thus be thought of as references to what the masses of a proton and the neutron are approximately the same. The mass of an electron is significantly less than that of a proton or neutron. The problem with discussing the masses of these particles is that they are now so tiny and one so little that any numerical values that we state for the mass in grams, the metric system unit of mass or weight, would likewise be so small that they would have little meaning to us. Scientists recognized this and decided to create a new unit for mass, the atomic mass unit, or mu, and arbitrarily defined it in terms of something very small, so that we could compare the one particle with another. And mu is officially defined as one the atomic mass unit, or mu, and arbitrarily defined it in terms of something very small, so that we could compare an article with another. The mu is officially defined as 1/12 the mass of a particular kind of atom, of the element carbon, the so-called carbon 12 atom, with the mu defined this way: proton-wise approximately 1 mu, neutron-wise approximately also 1 mu, and an electron-wise approximately 0.3055 mu. Next, we described the so-called electrical charges of these particles. Uh, the concept of electrical charge is still not well understood by scientists. However, we are familiar with the effects of charge. For example, lighting is the movement of charge through the atmosphere. Electrical current is the movement of charge through a conductor. The shock we feel when we touch a grounded metal object after sliding our shoes across a carpet floor on a dry day is the movement of charge from our body to the object. This static charge can be a hazard in a laboratory because it can ignite flammable substances, causing fires. In describing the charge of the subatomic particles that are part of the structure of all matter, and in order to explain their behavior, we assign each proton a charge of +1 and each electron of a charge of -1. They are thus equal but opposite in their charge, which means that they attract each other like the opposite poles of a magnet and can neutralize each other's charge. Open contact neutrons have no charge. How are these particles arranged within the atom? Much of the work of the scientists in the early 90s was focused on the question of modern theory of the atom. States that of the protons and neutrons are located inside an incredibly small core situated at the center of the atom, and that the electrons are located in the space outside the core. Obviously, the core contains most of the mass of the atom. Since the protons and neutrons possess most of the mass, it is very dense agglomeration of particles, often thought of a single particle itself. Scientists have named uh, named it the nucleus to give reasonable perspective on the nucleus in relation to the electrons. Imagine that the atom is a ball with the diameter of a football field. The nucleus would then be the size of a period at the end of this sentence, and electrons would take would take up the remaining space. Based on this description, if we look through the mythical microscope at a cross section of an atom, our view would look something like that, seen in figure 1.5. So see table 1.1 for a summary of the foregoing discussion. So we have figure 1.5 looking through the mythical microscope at a cross section of a single atom, an element. We would see that there is a tiny dense core called the nucleus at the center, where the protons and neutrons are found, and space surrounding the nucleus where the electrons are found. Microscope image from shutterstock.com. As you can see here, table 1.1 subatomic particles in an atom. We have particle, mass, charge, and location. For the proton, the mass is 1 mu, charge is +1, location in the nucleus. For the neutron, also the mass is 1 mu, charge is none, the location also in the nucleus. For the electron, the mass is 0.00055 mu, the charge is -1, and the location is outside the nucleus. For the number of subatomic particles, one very important compound of the study of the subatomic particles in atoms is the number of each of these particles within an atom. How one element's atoms differs from another elements atoms in terms of this number. Section 1.4.1, we indicated that the atoms of different elements are different from each other, noting, for example, that the size of francium atom compared with the size of hydrogen atom is like comparing basketball with the ping ball. Ping ball. Besides size, they are also differ in terms of the number of protons, neutrons, and electrons that each has. So, for the protons and electrons, let us refer back to the periodic table presented in Figure 1.2. We have noted that each of the elements in this table has an identifying atomic number, which is the number located in the upper left corner of each square. For example, hydrogen is number 1, nitrogen is number 7, calcium is number 20, and gold is number 79. We can define the atomic number of an element as the number of protons in the nucleus of an atom of that element. All elements differ in terms of this number of protons. In fact, the atomic number, since it is unique to a given element, is a primary characteristic by which an element is identified. If you do not know the identifier of an element, but you know the number of protons in the nucleus, its atomic number, you can look in the periodic table to determine its identity. See figures 1.6 and 1.7 for examples. In an electrically neutral atom, or an atom in which the number of positive charges equals the number of negative charges, the number of protons must equal the number of electrons. Thus, for a neutral atom, the atomic number is not only the number of protons in an atom, but it is also the number of electrons. An atom may gain and lose electrons, and that is why the number of electrons is not an identifying characteristics for an element like the number of protons is. An atom cannot lose or gain protons, particle that results from basic chemistry concepts and concepts. For the exercise, for the figure 1.6, so the information contained in a single element square in the periodic table figure 1.2 includes the element symbol and name, the atomic number, and the atomic weight. The atomic number is a whole number. The atomic weight is not a whole number, as you can see here. So 35453 is the atomic weight, and for the atomic number is 70. This is for the chlorine. For the figure 1.7, more examples of element squares from the periodic tables. The number of protons in nucleus is unique to each element, and so the atomic number, which is this number of protons, identifies the element. For example, if someone tells you that atomic number of a certain element is 47, you would know that the element is silver. The gain or loss of electrons is called an ion. The term ion was first defined in section 1.4.2. Additional discussion will be found in chapter 3. For neutrons and isotopes, the number of neutrons within an atom is quite variable, if even for different atoms of the same element. An atom of oxygen, for example, has 8 protons and 8 electrons, but it can have 8, 9, or 9 or 10 neutrons. Similarly, an atom of 9 has 10 protons and 10 electrons, but it can have 10, 11 or 12 neutrons. Atoms of a given element but differ because they contain a different number of neutrons, and the nucleus are called isotopes. The varying number of neutrons does not change the chemical identity of an element. It is oxygen or 9, for example, regardless of how many neutrons its atoms have. It also does not change the electrical neutrality because the neutron is not charged. It does, however, change the mass of the atom, since neutrons are important contributors to this mass, and it also changes a characteristic number called the mass number. The mass number is the sum of the number of protons and the number of neutrons in an atom. Mass number equals number of protons plus number of neutrons. Each isotope of a given element has the same atomic number but a different mass number. Example 1.1. What is the mass number of an isotope of magnesium if it has 13 neutrons? Solution: the mass number of the sum of the number of protons and the number of neutrons. The number of neutrons is given as 13. The number of protons is the atomic number of magnesium, which can be found in the periodic table. The atomic number of magnesium is 12, therefore mass number equals 12 plus 13 equals 25. Example number 2. Name the element described by the following mass. Number equals 19. Number of neutrons is 10. The atomic number, which is the number of protons, determines an element's identity, since the mass number is given and the number of neutrons is given. The number of protons may be calculated. Number of protons equals mass number minus number of neutrons equals 19 minus 10, and the total result is 9. So here we have the from the periodic table, we see that element with atomic number of 9 is fluorine. So we have the symbols for isotopes. Element name, mass number: carbon is 12, uranium is 238, curium is 239. A is referred to mass number, Z refers to atomic number, and X refers to element symbol. So symbols may be used to distinguish one isotope from another. One symbol that is frequently used is to write the name of the element, followed by a hyphen and the mass number. Thus, oxygen 17 is used for the oxygen isotope with 9 neutrons, and 922 is used for a 9 isotope with 12 neutrons. Section 1.5 would refer to the fact that the carbon 12 isotope is used to define an amine. This would be the isotope of carbon with 6 neutrons. See the left side table 1.2 for more examples. The right side of this table gives yet another type of symbolism for isotopes. The superscript is the mass number, and the subscript is the atomic number, and this symbolism. Moving to the atomic weight, isotopes occur in nature always in the same proportions. For example, consider boron, the element with an atomic number equal to 5. All boron atoms contain 5 protons, 5 electrons, but either 5 or 6 neutrons. Thus, 2 isotopes of boron exist. The isotope with 5 neutrons constitutes approximately 20% of the all boron atoms on Earth, while the isotope with 6 neutrons constitutes the other 80%. The source of the boron whether it be, for example, the United States or Africa, generally makes no difference. The ratio of one isotope to the other for boron is almost always between 20 and 80. The mass or weight of an atom is the sum of the weights of all the particles of which it's composed: protons, neutrons, and electrons. However, since the electrons' weight is negligible compared with that of the protons or the neutron, the mass or weight of an atom is nearly equal to the mass number. The more neutrons are there, the heavier the atom is, since all isotopes that occur naturally are always present in the same proportions, and since attempting to separate one isotope from another is not practical or useful in most cases, the atomic weight is almost always expressed as the average weight the of all the isotopes that exist. This average always reflects the proportion by which these atoms are found in nature. The atomic weight of boron, for example, is 10.811, not 10, the mass number of an atom with 5 neutrons, and not 11, the mass number of an atom with 6 neutrons. It's also not 10.5 or the average of 10 and 11, it is 10.811, a number closer to 11 than to 10. This reflects the fact that most boron atoms on Earth is 80% have a mass number of 11, and so the average is weighted toward 11. The atomic weight for any element is never a whole number. The atomic weight is the average weight of all the naturally occurring isotopes. The atomic weight is found in the periodic table. It is the number in the upper right of each square in the periodic table presented in figure 1.2. Once again, see figures 1.6 and 1.7 for up close examples. Important isotopes. Probably the most important set of isotopes are those for carbon. There are 3 main isotopes of carbon, one with 6 neutrons, carbon 12, B12 being the sum of the protons and neutrons, one with 7 neutrons, carbon 13, and one with 8 neutrons, carbon 14. Carbon 12 is the one which is used to define the atomic mass unit, as we have mentioned, as hence this isotope is considerable importance. Approximately 99% of all carbon atoms are carbon 12. The carbon 14 isotope is also a considerable importance. It is used in determining the age of materials found in archaeological discoveries. The element hydrogen has three isotopes: hydrogen 1, hydrogen 2, also known as deuterium, and hydrogen 3, also known as tritium. Deuterium may be isolated from naturally occurring hydrogen and is used in research studies in which hydrogen atoms change positions. Molecules, the movement of hydrogen atoms in chemical change process can thus be traced. Finally, there are a number of isotopes that are radioactive, such as uranium isotopes. This means that their atoms spontaneously break apart into simple atoms, which with time, this breaking apart is accompanied by dangerous radiation that is given off from the material in which these elements are found, and special precautions must be taken by technicians who work with them. For the homework exercise, the chemistry property and change, with what for aspects of matter is the science of chemistry concerned? How do chemical properties of matter differ from physical properties? Give 2 examples of each. Which of the following represent physical properties and which represent chemical properties? Iron bars, if Italian smells like and more balls. Potassium permanganate is purple. Density of gold is 19.3 grams per millimeter. Silver tarnishes. Hydrogen reacts with oxygen to form water. What is meant in chemistry by the term physical change? Give some example of physical changes. What is meant in chemistry by the term chemical change? Give some examples of chemical changes. Consider the change that occurs in each of the following. Tell whether it is a physical change or a chemical change and why. Sodium acidity method changes to a white solid. The presence of chlorine, yellow-green gas. A few crystals of sugar dissolves in the water in laboratory breaker. See, alcohol in liquid changes to vapor when heated. Which of the following represent a chemical change? Which represent physical change? Water is converted to steam by boiling. Carbon black powder is converted to colorless gas when reacted with oxygen. Salt completely dissolves in water to form solution that looks like ordinary water. When the chemical mercury oxide is heated in a test tube, a silvery substance condenses near the top of the test tube. When acetic acid is cooled below 16.7 degree, it is changed to a solid. So we completed the first chapter. We're gonna see the next chapter in the next video. So this is for today's video. Thank you for your time and see you on the next video.